Hey students, it's Mr. Mannix. Welcome to our part 2 of the Pulleys lecture. Remember, in this lecture we're going to talk about calculations a little bit more. So let's tackle some of these questions. What is the ideal mechanical advantage of the pulley in this system? Remember that the ideal mechanical advantage is determined by counting the number of ropes that would pull upward on the object you're trying to lift. In this case, there's only one rope right here pulling upwards. The other rope pulls down. This is a fixed pulley, which doesn't increase our mechanical advantage. So this system would have a mechanical advantage of just one. What does that mean? That would mean that if this was a 20 Newton box, which would be roughly a 2 kilogram box, by the way, then it would require a 20 Newton force to pull down on the rope to lift it. And if I pulled the rope down by 1 meter, this box would lift up by 1 meter. So how does this pulley make work easier? If I'm not increasing the force or the distance, why is this pulley useful? The pulley is useful because it changes the direction of my force. So that can be really useful. Let's say you're trying to lift something and you can't reach all the way up to the ceiling. You could attach a pulley to the ceiling, put a rope over it, and lift it up, or lower something down. Changing the direction can be very useful. Okay, we have another pulley here. What is the ideal mechanical advantage of this system? This time the pulley is a movable pulley. It's not attached and it will move upwards with the object. There are two ropes both pulling upwards on the object, so this has an ideal mechanical advantage of 2. The block has a mass of 10 kilograms. How much force must you apply on the rope? So remember our equation. Our input force times ideal mechanical advantage equals our output force. So knowing that, we know that input, I'm going to abbreviate that with I, times ideal mechanical advantage of 2 is going to be our output force of 10 kilograms. And by the way, we should probably convert this to a force, because 10 kilograms is technically a mass, not a force. So its weight in newtons, which is a force, force equals mass times acceleration. Force is equal to mass of 10 times the acceleration due to gravity of, it's 9.8. We're going to round that to 10 meters per second squared. So the force due to gravity of this is going to be about 100 newtons. So we're going to plug that in here. So instead of this, we're going to say that the input times 2 has to equal 100 newtons, and therefore we divide by 2 on both sides. My input force to lift 100 newtons would equal 50 newtons. Another way would be just to look at this and say it's a 10 kilogram or 100 Newton force. I just have to divide that by 2. Okay, what is the ideal mechanical advantage of the pulley above? Well, I'm assuming that these pulleys are fixed to a wall somewhere. And if we look closely, there's actually still just one rope pulling up on our box. So this still has, with all those ropes and pulleys, it still has an ideal mechanical advantage of just 1. If the box shown has a mass of 50 kilograms, how much force would you need to apply to the rope to lift it? You need to apply, you could hang another 50 kilogram mass from it, or you could apply a 50 kilograms times 10 meters per second squared is equal to a 500 Newton force. Okay, what is the ideal mechanical advantage of this pulley? Now we have two ropes pulling upwards. This has an ideal mechanical advantage of 2. If you pulled on the rope with a force of 25 newtons, how much tension would be in each section of the rope? Okay, that same tensional force is going to be spread throughout the whole rope. So actually, each section of rope still has 25 newtons. Now, how much force would the pulley exert on the weight if you exerted a force of 50 newtons on the rope? Well, a force of 50 newtons would be exerted everywhere In the rope, there are 2 ropes pulling upwards, so we take our force, 50 newtons, times our ideal mechanical advantage of 2 would equal 100 newtons. So let's go back to this second question really quick. If you pulled on the rope with a force of 25 newtons, how much tension would be in each section of rope? There's only 25 newtons in each section of rope. There's 2 ropes pulling up, so that would be a total tension of 50 newtons if they had asked you for the total. Okay, last question. If you lift the object by 1 meter, how much rope did you pull out? Well, our ideal mechanical advantage is 2. We're doubling our force, and that means for work to be conserved that we must have to pull this rope twice as far. So if we had to lift the object by a meter, 1 times 2, we'd have to pull 2 meters of rope. What is the ideal mechanical advantage of this pulley? There are 3 ropes pulling upwards. This has an ideal mechanical advantage of 3. How much force would you have to exert to lift a 20 kilogram or 200 Newton object? Okay, input force times the mechanical advantage is equal to the output force. So the input times 3 would equal the output of 200 newtons. So we're going to divide both sides by 3. And 200 divided by 3 equals 66.6 repeating, or 66.7 newtons. I would have to apply 66.7 newtons to lift a 200 Newton object. How far would you have to pull the rope to lift the weight 35 centimeters? Well, I have a mechanical advantage of 3, so 35 times 3, I'm going to have to lift it 3 times further. 35 times 3 is 105. I would have to pull 105 centimeters of rope to lift this object at 35 centimeters. Okay, now let's look at a little bit stranger pulleys here and see if we can figure out what the ideal mechanical advantage of these are. Really, we just have to remember the same concepts. Fixed pulleys do not increase mechanical advantage, and ropes have to be pulling upwards on the object to increase the mechanical advantage. So if I look at this, this is a fixed pulley, and this rope is pulling downwards, so it doesn't count. This rope, this rope, this rope, and that rope all pull upwards. So we have an ideal mechanical advantage in this pulley system of 4. All right, if we look at this one looks more complicated yet, but this rope here doesn't count. It's pulling downwards. And however, this rope is pulling upwards. This rope is pulling upwards. That rope is pulling upwards. All of these ropes are going to pull upwards. This would have a mechanical advantage of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, actually. This would have an ideal mechanical advantage of 10. That also makes sense because we have 1, 2, 3, 4, 5 movable pulleys, and each movable pulley doubles your mechanical advantage. So that has an ideal mechanical advantage of 10. All right, how about this one? This rope pulls downwards, so that doesn't count. This rope would pull upwards, and this rope would pull upwards. This one's actually not going to count, I don't think. This would just have an ideal mechanical advantage of 2. And what about this guy? There are 1, 2, 3 fixed pulleys, but there are 1, 2 movable pulleys, and there are 1, 2, 3, 4, 5 ropes pulling upwards and 1 pulling down, so this has an ideal mechanical advantage of 5. If I wanted to lift this crate 1 meter, I'd have to pull out 5 meters of rope. If I wanted to lift a force of a crate with a 500 newtons of weight, I'd have to pull with a force of 100 newtons. And okay, those were all of our sample calculations using pulleys. Tune back in for our next lecture on our other simple machines.